So hello everyone, this is lecture 4 for the nuclear physics. In the last lecture, we were studying that how can we find the radius of the nucleus using the mirror nuclear methods, and we saw these, and we find it two methods. First, we see that during the transition from the one mirror nuclei to another, we see that there is a difference in the Coulomb energy that gives us the binding energy, and we just put or substitute it equal to this formula, this one, and we can get the radius. And we find another method also, where we know that if we know the maximum kinetic energy of the beta particle, then we can just apply this formula and we can find the radius of the nuclei. So based on this, we have two examples. So this kind of question can be asked. First is difference in the Coulomb energy between the mirror nuclei, that is Cr 2449 Mn 2549 is 6 mega electron volt, assuming that nuclei has a spherically symmetric charge distribution and that E square divided by 4 pi epsilon naught is approximately 1.0 mega electron volt Fermi, and the radius of we need to find the radius of this nuclei. So what will be the radius? So we know that this delta E energies must be equal to the change in energy of Coulomb energy. So we just substitute 6 mega electron volt equal to this. We know Z1 and we know Z2. We just substitute the values, and we know that this E square of 4 pi epsilon naught is given as 1 mega electron volt. When it is not given, then we will consider the value as 1.44. But when it is given that it is 1, we will take it as 1, and we'll solve it for the R. We will get the 4.9 Fermi as the radius. So that's how you can just directly use this formula and the Coulomb energy, and you can calculate the radius. Next is Cl1733 decays by positron emission with maximum energy of 4.3 mega electron volt. We need to calculate the radius of the nuclei. So we need to have the maximum energy, that is 4.3 mega electron volt. Now we have this one, we have this energy, and we need to substitute this equal to this. So, and we need to find the radius, so we will use this formula, not the previous one. So here just substitute this equal to this. We know already the value of these. This will remain same, that is 1.29 0.51, and this E beta max is given as 4.3. Substitute these values and find the value of R, that will be 4.67 Fermi. So only this kind of question will be asked from this section. Now we will move on to the nuclear probes. So what is our probe? Probe is an investigation, and nuclear probe means there is an investigation inside a nucleus. So we use various methods to investigate inside the nucleus, that different kind of beams, that can be electron beam, photon beam, proton beam, neutron beam are used. So these are called the nuclear probes. In order to study nuclear size, shape, charge distribution, mass distribution, etc., electron beam, proton beam, neutron beam are used, and they are called the nuclear probes. So what is the criteria to choose the nuclear probes? So we have electron beam is there, and we have this nucleus, and we will just apply this beam on it, and we'll see that there will be scattering. And how can we define this scattering? So see, there will be a wave associated with every electron, and if there is wave, then there will be, we can just see this as a diffraction, means there is this obstacle and there will be this diffraction. So for the diffraction, what we know, that diffraction occur only when the wavelength of this particular radiation is equal to the size of this obstacle or less than the size of the obstacle. So what is size of this nucleus? That is 2r. So scattering as the diffraction of the wave by the obstacle. So lambda must be equal to the wavelength of this must be equal to 2r, that is the dimension of this obstacle, that is nucleus. So only this wave can be used which have the lambda equal to 2r. So this concept we will use to find the, means what kind of radiation or beam we can use, means we must first find the r, then we can find the lambda, and that's how like when we have lambda, then we can find this momentum also of this particular wave, and we have this momentum, then we can just use any beam and we can just apply the energy equations, that this particular proton beam must have this much energy or that much energy. So if we know the momentum, we can just find the energy which is required for this beam to investigate this. When particle beams are acting as a nuclear probes, then de Broglie wavelength of the probe should be less than or equal to the size of the object being investigated. So lambda must be equal to less than equal to 2r, and lambda is nothing but h upon p from de Broglie. From here we can find the p must be greater than equal to h upon 2r. So this momentum must be, the momentum of this wave must be greater than equal to h upon 2r. So we have momentum, so we can find the kinetic energy also, that how much minimum energy is required to probe this nucleus. Now there will be two cases. There was first a relativistic case, non-relativistic case. So in relativistic case, we know that kinetic energy of this particular wave, can you find it as total energy minus the rest mass energy. So total energy can be calculated from p square c square plus m naught square c4. So we know p. So we just substitute it here and find a total energy minus this rest mass will give you kinetic energy. But when it is non-relativistic case, this will be simply there will be no potential energy and simply it is p square by 2m. So you have v, p, you can find the total kinetic energy, that will be this. Now see how can you find this energy. Now for that you must need the r. With the help of r you can find the lambda, and lambda will give you p and p will give you these things. So for that, if you just know the atomic mass or the mass number, you can calculate the r because r depending on this. So that's how the question will be framed, means you first calculate the r with the help of a, then you will find the p and you can find the energies and all. Okay, we will see some question based on this, but before that let's see the different beams separately. First we have electron beam. So how it is useful? So see, we have electron beam, it will interact with this proton or the nucleus in two ways. Means first there is this charge on these two particles, so there will be EM interaction. And see, these electrons are nothing but leptons. We will study in the nuclear particle physics about these leptons and all. But here you must know that these leptons are just interact them with weak, means this interaction is weak interaction for the leptons. But for the proton neutrons, they are nucleons and they interact with strong. Their interaction is strong, so it will be strong interaction and EM interaction. So here this electron will interact with this proton with the EM, and the only EM interaction will be there. There will be no strong interaction because these are leptons. So there will be only one interaction available, and we can just accelerate this electron to any energy using the accelerators. Means just apply the potential difference and this will accelerate the electron. So we can just in various ways, this results will be very helpful and easy to observe from the electron beam. So that's why this electron beam are very much used in the practical situations. Electrons are suitable probe to study the distribution of charge inside the nuclei because electron interact with the nuclei only, so the EM interaction, not the strong interaction. For this purpose, the high energy electron beam having energy of that order of 100 to 500 mega electron volt is required. So see, because of this property that it will interact with only EM interaction, and we can accelerate electrons. So this will be very useful beam which we use in the normal experiments. But there is one more, this is proton beam we also can use. With the proton, if we see that there will be strong interaction and EM interaction, both will be there because proton is again a nucleon and it is you are applying nucleon on the nucleon, so there will be strong interaction and EM interaction also because of the charge. So now there will be a scattering result which will be hard to judge or differentiate because both interaction will be there. So interaction between nuclei and protons can be used to study the nuclear structure because this is also nucleon, so you can use it to study the structure or the how neutrons and protons are distributed inside the nucleus. So interaction between nuclei and protons can be used to study the nuclear structure, distribution of nuclear matter, shape as well as for charge distribution. So we can use this proton beam for these things. There are two main disadvantages of proton nuclear scattering, so you must remember these disadvantages for the interview purpose. So it is difficult to analyze result because both strong and EM interaction are responsible for the scattering, as I told you. Next, it is difficult to create proton acceleration facility for high energy protons. So it is very difficult for the accelerators like to accelerate the protons, but it was easy for electrons to accelerate them. So next is neutron beam. Now see, this is a very helpful thing, neutron beam, and it can be used very efficiently, but there will be disadvantages for the neutron beam also. So neutron beam is simply neutral particles, so there will be strong interaction because this is a nucleon, so only one interaction is there, so it is easy for us. But see, you can't accelerate neutrons because it is a neutral particle, that's why you can't accelerate. And after interaction you can't just study the scattering because neutrons are the unstable particles and they just break down into the protons, so that's why it is hard to observe after the scattering for them also. So neutrons can be considered as a better probe than protons because here scattering will take place only through the strong interaction, so it will be relatively easy to explain the results. Neutrons can interact with protons as well as neutrons, so strong interactions. So this probe can be better utilized to investigate the distribution of the mass inside the nucleus. This is all what I already told you. However, means what are the two main problems with the probe for the neutron beam? So it is difficult to produce high quality neutron beams with high energy because neutrons are neutral particles, so you can't just high quality neutron beam you can't produce. And neutrons are unstable particles because they just turn into the protons. It is difficult to detect neutrons after scattering for the same reason. Now what kind of question can we ask from here? Now see, what should be the kinetic energy of proton to probe the size of 4020 Ca? So you need to find the kinetic energy. So you must for that first you need to find the lambda or the momentum, only then you can find. So for the momentum you must need the lambda, and for lambda you need its mass number, that is 40. So rest mass energy is given as 938 mega electron volt. So we need to find the kinetic energy. So first find the R, that is R naught A 1 upon 3. So we know A, that is 40, and R naught is 1.2 into 10 to the minus 15. This will give you R. Now 2R is the size of the atom. So that will give you the lambda. Lambda must be around the size of 2R. So that's how you can find the lambda. Now lambda is h upon p. From here you can find the p, that is h upon 2R. Now you have p, so you can find the pc, that will be 154.69 mega electron volt. Now see, to check that whether it is a relativistic case or not, you just compare pc with the rest mass. So pc and rest mass, if pc is very much less than rest mass energy, then you will call it as non-relativistic case. But when pc is around m naught c square, or pc is greater than m naught c square rest mass, then you call it as relativistic case. So see here, 154.69 is not negligible as compared to 938. So we must consider it as relativistic case. So we will first find the total energy, then we will just minus the rest mass energy. That will give us the kinetic energy. So p square c square m naught square c4. Just substitute the values, and you will get this. So total energy will be 950 mega electron volt. So kinetic energy will be E minus m naught c square. That will give you 950 minus 938. That will be 12 mega electron volt. So this will be your kinetic energy. So you must know that when it is relativistic and when it is non-relativistic. So you must know this. Next is distribution of charge inside the nuclei. Now we need to study that how charge is distributed inside the nuclei. On the basis of various experiment results, the following pattern of charge density is observed in the nuclei. So this was observed, means on the various experiment was done, and then you get this graph. So this is the charge density, and this is the radius from the center. So as the radius increases, first the charge density remains constant, and then at the boundary you will see that there is no abrupt boundary, means there is no sharp decline. This is like this is decreasing. This is a diffused boundary is there, means charge is decreasing slowly. Okay, so this is not an abrupt boundary, this is a diffuse boundary for the nucleus. Like at the boundary of the nucleus, you will see charge is not directly becoming zero, it is decreasing slowly, okay, gradually. So that's why, and this reason behind this is nothing but because these particles are microscopic particles and these are quantum particles. So there is the probability of finding the particles around this, so that's why that probability decrease like this. Okay, so if this is a classical case, then this must decrease abruptly or sharply, but here it is a quantum case, that's why it is decreasing like this. So to define this curve, there was this formula given by the Wood and the Saxon. These were two scientists. So this formula was for the density, charge density, that is given as rho naught divided by 1 plus exponential r minus r by a. So what is this a? This a is called the surface thickness, means this is the distance from the diffuse boundary. You will see that when the charge density becomes 0.9 rho naught or 90%, and it is decreased to 10%, means at the boundary when the density decreases from 90%, initial 90% to the 10% initial, that particular space is called the surface thickness, or a. Okay, so you will see that if it is rho naught here, and it is becomes 0.9 rho naught here, then 0.1 rho naught here, so this distance is called the diffuse boundary or the surface thickness. Okay, so that's how you can find the value of a. So that's how you will define where rho naught is the charge density close to the center. Rho naught means rho naught is the density at center, close to the center, and this will decrease like this with the help of this formula. So a is called the surface thickness, or this rho naught value is around 0.15 electron per Fermi meter cube. So this is the charge density, that's why it is Fermi meter minus 3. A is called the surface thickness or diffusiveness of the boundary. It is considered as the radial distance over which charge density decreases from 90% to 10%, as I told you. So normally in the observations or the observatories, laboratory, you can see that they have provide the data here, and you can just observe this graph, or you can just divide this whole values by rho naught. You will see that it is 1 and 0 and 0.9 to 0.1. That's how you can calculate this surface thickness also. So in the next lecture, you will see that how charge is distributed inside the proton or neutron also. Then we will move forward to the binding energy and all. So that's all for today. Thank you everyone.